Hi, I'm Alexander Urena.
Hi, I'm Videshi Mitta.
And I'm Diego Brown.
I'm Morgan Chi. And today we're going to present on topological groups.
Yeah, so we're group 6 and we were assigned topological groups, which is really just additional exercises. So in order to talk about topological groups, we first need to know what a group is. So a group is simply a set that has a few criteria that it has to meet. So let's see what the criteria for a group are. The criteria for a group include a few things. We need an identity element. We need it to be closed under the group operation. So really a group is a set along with an operational group. And we're going to get to a few examples right after we get down all the requirements. And there has to be an inverse for each element inside of the set and under the group operation. And then finally, but not least, we need the operation to be associative. So we're going to go through a few examples right now to make sure that we fully understand what a group is. So the first example we have is going to be, Z under addition. Is that big enough for you? Cool. Okay. So first we need to check to satisfy that there's an identity element in Z. We need to check that it's closed under addition. That's the group operation that we're considering. And that there's an inverse element for each element in Z, in the integers. And then we finally need to check that it's associative underneath addition. This is probably fairly obvious, but it gets a little bit more nuanced when we consider different sets. So for the identity element, we obviously know that 0 is an element of Z. That is, if you take A, B, C, element of set Z, we know that A plus 0 is simply just equal to A. In that sense, we have the identity, so the first requirement is met. So, identity. We can put a check mark by that. Now we need to check that's closed under the group operation. This one's pretty trivial. If you have two integers, you end up with another integer. So if you consider A and B, then you know that their sum, A plus B, is also just an element of Z. That is, for example, if you take something like 2 and 3, you just end up with 5, which is just another integer. Now, to check the inverse. So simply just consider A as an integer. Well, we know that the negative of A is also an integer, so it's closed. So there's also an inverse, just simply negative A. As we see, A plus negative A is simply equal to 0. And that's all it means to have an inverse, that we simply get the identity once we add together everything. So we finally have the inverse, and then we finally show associativity. So we want to check that if we have two things, yes, so actually if we have, okay. So for our group operation, we want to show that for our 3 A, B, and C that are integers, that addition is associative. That is, A plus B plus C is equal to A plus B plus C, which is just a property that the integers has under addition, as we know. So this would be a group since it satisfies all these 4 criteria. And then we'll give we'll just give a couple more trivial examples. So we will now consider set R under addition. Well, R under addition is quite similar to the case with the integers. We know that the negative of each element is also part of R. And so the rest simply follows the same for the integers. So we will actually skip to a more slightly complicated example, but not too difficult. So this is going to be R plus, with the group operation here just being multiplication, where R plus is simply just going to be all the positive real numbers. So now we must check that there is an identity. So for A, B, and C, elements of R plus, we need to know if there's an identity, and there is an identity. So the identity here is just going to be 1. That is, if we take A, element of R plus, we know that 1 over A, when we multiply A and 1 over A, we'll simply just get 1. So now we'll move on to it being closed. So if you take two positive real numbers and you multiply them, well, if you multiply two positive numbers, you simply just get a positive number. So we know that this is closed. So A dot B, where these are both elements of R plus, just simply yields a new positive number. So it is closed. Now for an inverse, this is what we were referencing earlier with regard to getting the identity. And if you simply just have a real number A, its inverse is just going to be 1 over A. So you have A multiplied by 1 over A, gives you the identity, which is simply 1. So we have an inverse. And finally, for associativity. For associativity, it works the same way. So if we have A multiplied by B, all multiplied by C. Well, since we know how multiplication works with real numbers, we know that it simply is just associative. So this is A times B times C. And there we've shown that these examples are groups. Now we need to move on to the notion of what a topological group is. So for a topological group, we just have to add, we just need a group that is also topological space. So formally, let's write here, a topological group. We will be coming back to this definition a lot throughout our presentation, so it'd be useful to write it down. G is a group that is also a topological space, so that there's some sort of topology on it. This topological space which satisfies the T1 axiom, which is T1. So finite sets are closed. That's just simply what it means to satisfy the T1 axiom. And we also need that the map G cross G into G sends X cross Y, so simply an element XY, to into X dot Y. We write dot here, but it doesn't have to be multiplication, it's simply just the group operation. So this map must be continuous, and along with that, another map is also gonna have to be continuous. So the map G cross G into G, sending some X and Y in from the group G to X group operation Y. This has to be continuous, and one more map will have to be continuous. And then the map of G into G, sending X into its inverse, must be continuous. Okay, and this is all that it means to be a topological group, that we have a group which is a topological space, and that the map G cross G into G, which sends two elements X and Y into X group operation Y, and the map that sends some element X of G to its inverse, these two things must be continuous. And notice we are guaranteed an inverse because we know that we're working with a group, and the group operation here, it doesn't simply have to be multiplication even though we've written dot. Furthermore, a critical component to having a topological group is that it has to be T1, so finite sets are closed. This will help us in the following proofs. All right, you guys want that? And
Can
then
we cut the recording for a second?
We have seen some examples of groups, but the examples we have seen are all infinite groups. But a group doesn't have to be infinite. There are also a lot of examples of finite groups. And one example is called the dihedral group, D2. And to explain what that is, let's take a concrete example where, let's say that n equals 4. To imagine what the group does, it's very helpful to see a picture. Suppose we have a square and then some labeled vertices, A, B, C, D.
What did they say?
The dihedral group, D2 times 4, which is D8, basically contains all the operations you can do to the square such that it remains a square in this configuration, but up to the rearrangement of indices, which basically means that you can rotate the square by 90 degrees, by 180 degrees, 70 degrees. Well, of course, you can rotate it by 60 degrees, but that's doing nothing. We can also reflect it in the x direction and reflect that in the y direction. And for here, we'll denote a 90-degree rotation in the counterclockwise direction by r. So r is the same as 90-degree rotation counterclockwise. Since 180-degree rotation is simply the 90-degree rotation applied twice. So in the set we have r squared. 270 is 90 degree applied 3 times, and 360 is r to the 4th, but that is doing nothing, so we denote it as the identity E of our group. We can have r to the 5th, but that doesn't add anything because rotating 90 degrees 5 times is just rotating 360 degrees, which is doing nothing, and then rotate 90 degrees again. So r fifth is equal to r. We also have this reflection S, which is reflection across the x-axis, the y-axis actually. Here, this is S. But do we need another element for this? Well, in fact, we don't need to introduce another new element. We can just get this by composing R and S. To see that, just consider doing the following operation. we have A, B, C, D. What we want to get is a reflection across x-axis, which is A, B, C, D. We can get that by directly applying a reflection across the x-axis, but just with the rotation and reflection across x-axis, we can actually reach the same result.
Really? Yeah, because I see him a few times.
First, we can do a rotation across the y-axis. That gives us A, D, C.
Oh, yeah.
And then we simply need to do a 180-degree rotation. So this is S,
Yeah, he actually.
this is square. And you'll see that after rotating, A becomes here, B, C, D. So you basically rotate A here, B here, B here.
Also,
You can see that. So basically, we don't need an extra element to denote the reflection across the x-axis. R and S will suffice to show all possible transformations one can make. And in particular, that one is SR squared. We can also have SR and SR cubed. And that basically is all our elements that we can make from R and S, because adding another S will make it identity, because S squared reflecting twice is doing nothing. R to the fourth is also doing nothing. So this is a complete list of our group elements, or the things that I call group but haven't proven is a group yet. So next I have to prove that this element, this set actually forms a group. And we need to check the conditions for a group. So identity is just E, which is doing nothing. That's easy to see. We need to have close. Well, any R and S preserves the shape of this square, so you can compose them whatever way you want, and the result will still preserve the shape of the square. So this is automatically true by our construction. You need inverse. In particular, we need R inverse and S inverse. And once we have those, we can just construct the inverse of the things, everything else. Well, what's the inverse of R? R is 90-degree rotation clockwise, so the inverse of R should be 90-degree. R is 90-degree counterclockwise, so the R inverse should be 90-degree clockwise. But a 90-degree clockwise rotation is the same as 270-degree counterclockwise rotation. So the R inverse is just R cubed. And S inverse is just S, because when you do a reflection twice, you do nothing. And with these two things, you can get the inverse of all other elements, because they're just combination of R and S, using the fact that the inverse of let ABC be R and S, ABC all the way to Z. I don't know, whatever how many you want, doesn't matter. Using the fact that the inverse works like this. So you can define the inverse of all elements. Next we have associates. And we have to discuss case by case. If we have S, R, is that the same as S R squared? Well, we can just check that. what is SR, we start with anything. We start with Q, A, B, C, D. Well, we first go through R. Remember that group, the transformation goes from right to left. Goes through R. And then you go through S dot R, the combination. But we first need to check what S dot R does too. So S dot R right here. You kind of already can see that this is going to be automatically true. The associative is going to be automatically true because to get S dot R, you still just first perform R. And then you perform S. So here, so we can just apply the rule here. We see that this vertex is fixed, and so is this vertex, and these two vertices are switched. This is SRR, so what about SR squared? Well, we start with the same square. Get A, B, C. And then a reflection. A, B, C, D. So indeed, they get the same answer. And this is a pretty general case because we involve both S and R. If all we involve is S or R, then you can easily check that a bunch of rotation is the same no matter how you divide them, and a bunch of reflection is the same. So we have checked associativity. So it turns out that this dihedral group is indeed a group, and it has exactly 2n elements, and that's why we call it D2n. So that's an example of a finite group.
All right, so before we get to solving any of our important problems, we need to consider some really, really fundamental theorems and lemmas that'll make our lives much easier when considering these problems. So we have two theorems and one lemma here. Lemma 21.4, the addition, subtraction, and multiplication operations are continuous functions from R cross R to R. And the quotient operation is continuous function from R cross R subtract 0 into R. So this lemma follows pretty simply from the epsilon delta argument that you've probably seen in analysis. In that sense, it's very trivial, that's why it's only a lemma. For theorem 19.6, so we let f be a function from some set A to the Cartesian product of x sub alpha guys, where alpha is index set of a j, or j is an index set, we're pulling alpha out of j. So we let f of some element A be given by the coordinate f sub alpha of A, where again, alpha is just picked up an index set. So as long as these f sub alpha functions from A to x sub alpha for each alpha. So let our Cartesian product of x sub alpha have a product topology, then the function f is continuous, this f, if and only if each function f sub alpha is continuous. So we will use an example further in our proof where, so we'll use an example further in our proof where we apply the identity to the first coordinate, which is going to be a continuous function, and then we apply another function which we, by our assumption, is going to be continuous. So it's going to meet this requirement for this theorem in order for the overall function to be continuous. Next theorem is 18.2. We use part C and D. So let x, y, and z be topological spaces. First, we're going to use the composites. as long if f is a function x to y, and g is a function from x to z, if both these functions are continuous, then the composite g to f from x to z is also continuous. The idea here is that you simply just take an open set and you move it through each topological space, and the result follows almost immediately. Now, when it comes to restricting the domains, if f is a function from x to y and is continuous, and if a is a subspace of x, then the restricted function f restricted to a from a to y is also continuous. And that's all the theorems we need to progress to our next problem.
Yeah, number one. So number one says, let H denote a group that's also a topological space satisfying the T1 axiom. Show that H is a topological group if and only if the map of H cross H into H sending X cross Y into X dot Y inverse is continuous. So So this is what we're trying to show. We're going to show first if 1, then 2, and then if 2, then 1. And we're going to be using the definition of a topological group given before. So we start by assuming 1, and that tells us that and then that same definition of a topological group also tells us and we know that this map is continuous by our definition of a topological group and theorem 19.6. Now, since we've defined functions f and g, we can compose them to be which we can say is continuous by theorem 18.2 C. And then since this function that we compose is continuous, that's what we're trying to show in 2. So that completes our proof in one direction. Okay, now we're gonna assume 2 and work our way to 1. So if we assume 2, then we know that so we know that this map is continuous by assumption. Then we can restrict H to and we can say that this is continuous by theorem 18.2D, which tells us that the restriction of a continuous function is continuous. Then, since our restriction is isomorphic to H, we let the map be continuous as well. And then we take the composition of H and G, which is, or wait, we first define G, H cross H to H cross H. Which is continuous. And then we can take the composition H of G continuous. And since we've defined both this function that's continuous and this one that's continuous, that's our definition of H being a topological group. So we have 1, and we're done.
Okay, so as Alex showed here in A and C, we've shown that these two are groups, but we haven't yet shown that they're topological groups, so that's what I'm gonna do now. So we've seen over here the condition for what a topological group is, so now we just need to show these three conditions. So the first condition I'll call 1 is we need to show that Z is T1, which is easy because Z is a subset of R and R is T1, so that automatically makes Z T1. Secondly, we need to show that the operation, so sending Z cross Z into Z, where we send 2 points A and B into A plus B, we need to show that that is continuous. And we will show that via theorem 21.4, which shows that addition with the real numbers is continuous. So we want given by the 2 points A and B mapping to A plus B, and this is continuous by theorem 21.4. And then similarly, we want to show that the map from Z to Z, taking A to its inverse, is also continuous, which similarly can be shown by the exact same theorem 21.4. So we'll show that here. So we have satisfied all the conditions for topological groups, so we now know that Z with addition is both a group and a topological group. So now we need to show the same thing for C here. Once again, condition number 1 is met because R plus is yet again just a subset of R. So it is also T1 by definition. And similarly, the other two conditions are shown by the exact same theorem 21.4, because 21.4 demonstrates that multiplication with real numbers is continuous. And then we have another group, which is, what was it? It was R with addition, correct? This is once again very similar, so I need to show that it's a group as well since we haven't shown this one yet. So first, the identity element is obviously 0, which is in R, of course. This proof follows very similarly to showing that A is a group. So next we have closed. If we let A, B, and C be just real numbers, then we have that A plus B is, we have that A plus B is still a real number because the real numbers are closed under addition. And then we need the inverse. For any element A, we have A inverse, which is simply negative A, because A plus negative A equals 0 for all real numbers. And then finally, we need to show associativity. So we have A plus B plus C is equal to A plus B plus C. And we know this just because addition with real numbers is associative. That's a pretty elementary fact. So now we need to show, we've shown that R with addition is a group. So now we need to show that it's a topological group. Once again, R is a subset of R, obviously. So it's T1. And then once again, by theorem 21.4, addition in the real numbers is continuous, and taking inverses in the real numbers is continuous. Okay, so the next group, the next topological group we need to check is D, which is the set S1 with the operation of multiplication. So what is S1? S1 is the set of all numbers e to the I theta such that theta is just a real number. So you might recognize this as the set of all complex numbers with modulus equal to 1. So first things first, we need to show that this is a group. So first is the identity. Simply let theta equal 0, which we can do because it's just a real number. So we have that, which equals e to the 0, which equals 1. And with the group operation of multiplication, of course, any complex number multiplied by 1 is going to be equal to itself. So we've proven that. Next, we have closure. So let's let Z1 equal e to the I theta 1, and let's let Z2 equal e to the I theta 2, and we're going to multiply them together. And then following simple exponent rules, we have the I theta 1 plus theta 2, which of course is just a real number again, so we're still in this realm of S1, so it is closed. Next we need the inverse. If we have Z equals e to the I theta, I'll propose that its inverse is equal to e to the I negative theta, so that when we do Z times Z inverse, we get e to the I theta minus theta, which is just 1, which is what we wanted. So that shows inverses. Next, we have associativity. So let's let A, B, and C, actually, let's let this be Z1, Z2, Z3, be elements of S1. Then we simply have Z1 times Z2 times Z3 being equal to Z1 times Z2 times Z3. And this is true because just multiplication in complex numbers is associative, so that's proven. Now we need to show that it's a topological group, so we need to do those same three conditions again. Okay, so now we need to show that S1 with multiplication is a topological group and not just a group. So the first condition, we need to show that S1 is T1, and it helps to think as S1 is simply, because any number Z in S1 can be written as the form A plus BI. So simply every Z can be expressed as an ordered pair AB, which means that S1 is a subset of R2, and we know that R2 is T1, therefore S1 must be T1. For the second condition, we need to show that the map S1 cross S1 to S1, sending Z1, well, the ordered pair, Z1, Z2 to Z1, Z2 multiplied like that is continuous. And the way we show that is we let Z1 equal e to the I theta 1 and Z2 e to the I theta 2, and then their product Z1, Z2 is e to the I theta 1 plus theta 2, which can be rewritten as equaling, it would be cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And in this case, we have that using the trig identities for angle sum, we can re-express this term as multiplication of cosine of theta 1 and theta 2 plus, or subtracting out sine terms, was it? Yeah.
Also multiplication of cosine sine.
So, and those operations are continuous by theorem 21.4. So we have composition of a bunch of continuous functions, so that in itself is continuous. I need to put more space, so we go over here. So then, for number 3, we need to show that the one going from S1 to S1, taking Z to Z inverse is continuous. So we let Z equal e to the I theta. Z inverse is simply e to the I negative theta. And once again, we can use the same trick as before. So simply letting Z equal cosine theta plus I sine theta and z negative 1 equaling cosine of negative theta plus I sine of negative theta. Once again, this is composition of continuous functions, and that in itself is continuous. So I believe we are done by theorem 21.4.
And you just have to pull the negative sign outside of, in cosine you can just disregard that, and in sine you put the negative sign in
Yeah.
front.
We can do that. And do that. And we should be good. Correct?
Yeah.
Yeah. Okay, so we'll move on to the next group now. So our fifth and final group, E, is the group, or the set, GLN with matrix multiplication. So what is GLN? GLN is the set of n by n non-singular matrices. Yes, and this is simply just matrix multiplication. So first we need to check that this is a group. So we check the identity first. That is simply the identity matrix with dimension n. And if you remember linear algebra, by definition, if we let A, B, and C be elements GLN, by definition, INA is equal to AIN, which is equal to A. So that is the identity. Next we have closure. So we want to show that AB is an element of GLN, just with how matrix multiplication works. This is also going to produce, this operation AB is also going to produce an n by n matrix, and it will be non-singular because the determinant of this matrix will be the determinant of A times the determinant of B. So those are both non-zero by definition, so it'll be non-zero for AB, which will make it non-singular. Next, we need inverse, which is rather easy. By definition, the matrices in GLN are non-singular, so their inverse exists. So we know that A times A negative 1 is equal to A inverse times A is equal to IN. And associativity finally. We want to show that ABC is equal to ABC, and matrix multiplication is associative. This is just a fact we know from linear algebra. So this is done. Next, we've shown that it's a group, so now we want to show that it is a topological group. So condition 1, we need to show that it's T1. If we just simply think of GLN as, we can think of GLN as being a subset of Rn squared. And if we think about it that way, then this is T1, which implies that GLN is T1. So the next condition we need to show is that GLN cross GLM going to GLN of taking two matrices A comma B into A times B. We need to show that this is continuous. So in order to do that, let's visualize it first with two kind of generic matrices. So let's say A is equal to, let's just say it's A, B, C, D. And we'll say B is equal to E, F, G, H. Simply, when we look at the multiplication here, we know that AB is equal to AE plus BG in this first coordinate here. So as we can see, it's simply, in each coordinate, it's simply composition of multiplication and addition in the real numbers. So we know that in each coordinate it would be continuous by theorem 21.4. So the entire matrix multiplication operation is continuous by 21.4. And then condition 3, we need to show that GLN taking A inverse, we need to show that that is continuous. So the way we do that is we use the fact that A inverse is equal to the adjugate matrix of A divided by the determinant of A. And so then we want to examine adjugate of A in greater detail. So let's take, for example, if A were to be a 3 by 3 matrix, A, B, C, D, E, F, G, H, I, then the determinant of A would simply be A times the determinant of E, F, H, I minus B times the determinant of D, F, G, I plus C times of D, E, G, H. And then, as we break this down more, we see that A times EI minus FH minus B times DI as you can see, even if we were to scale up or scale down this matrix, this pattern of repeated determinant taking would continue, and in the end, it simply devolves into multiplication, addition, and subtraction, which are all continuous by lemma 21.4. So in the end, this is continuous, which means that taking the inverse is continuous. And one more thing we need to show is that the adjugate of A is continuous as well, which just by definition of the adjugate, it's just once again a composition of elementary operations, which makes it continuous by lemma 21.4.
So in problem 3, we want to show that if G is a topological group, and H is a subgroup of G, we want to show that H and H bar, which is a closure of H, is also a topological group. Well, first let's show it for H. We already know that H is a group, so there's nothing to show on that part. We need to check that H is a topological group, and by what we get from problem 1, we only need to show that the function is continuous. We only need to show that f is continuous. But we know that f here is simply a restriction of the same function in G. So let me write f of h here. But f of h, well, it's just f restricted to h. So we know that this function is continuous, and because of that, h is a topological group by the conclusion we drew from problem 1. And next, we need to show that h bar is also a group. Closure of h group. Well, we need to check that it has the identity, it's closed, it has inverse, and it's associative. But most of it we can just get by inheriting the group multiplication from G, specifically associative. Associative is trivial because we know that the group multiplication is associative in G. So we just need to check that well, first we need to check that it's closed, which is to show that we need to show that this function has a property that when acts on h bar plus h bar, we still get an element in h bar. And we can show that by using theorem 19.6, which says that the product of closure is the closure of product. We want to show this. By 19.6,
Fortune 500.
we know that this is the same as h cross h closure. And since we know that f is continuous in G, using one of the equivalent definition of continuity, we know that f of anything closure is the f of that set closure. But since H is a group, we know that f acts on H cross H, gives something inside H. So this is a subset of H, which is what we want to show. We can also show this using pictures. So let's imagine H H doesn't have to be closed. We can have some open parts. So the entire space is G. And H doesn't have to be connected, so we can have like disconnected parts as well. So for instance, consider the group like ON, the orthogonal matrix, M by N matrix. Those are not connected, and that's because you can either have determinant 1 or determinant -1, and you cannot continuously evolve one into the other. So in general, H can be disconnected. And what we want to show is that for any 2 points, let's say one here and one here, the group multiplication still sends it inside to the closure of H. So let's say that the group multiplication sends it somewhere. We don't know whether it's inside or outside yet. We can take an open neighborhood of this point, and then we can take the pre-image of this set. Because we know that F is continuous, the pre-image must also be continuous. There'll be some open set here and some open set here. Now, since these 2 points are in the closure of H, we can always find points inside. We can always find intersection of the open neighborhood with the closure, with the set itself. And if we just apply the group multiplication here, we'll get something inside here. But because of the continuity of H, as shown here, we must have a point inside the set for this neighborhood. And as we can see, if the point is chosen outside, then we cannot meet this criteria, which means that the only possible place that the group multiplication can send 2 points is also in the closure of H, which is what we want to show. Only in this case, we can guarantee that any open neighborhood of this point has an intersection of it with H. So now we show that this is closed. From here, we can easily show that we have an inverse, because if we want to find an inverse of any element, then we simply let X equal to the identity and Y be the element that you want to find the inverse. And you get the identity times Y inverse, which is Y inverse, what you want to show. And we know that Y inverse is inside H bar. So then we basically check that H is a group, and then to check that H is a topological group, H bar is a topological group, we follow the same argument as H, because this function F restricted to H bar is continuous because F is continuous in G, which means that H bar is not only a group, but also a topological group.
Yeah. So in this problem, we've been given 2 functions and we've been instructed to show that they are homeomorphisms. So the functions we've been given are so in this way, F is multiplying by alpha on the left and G is multiplying by alpha on the right. And we want to show that F alpha, G alpha are so, in other words, that they are bijective, continuous, and open.
I would live anywhere else.
Okay, so we've determined determined what we want to show, so now let's begin showing it.
It's crazy though.
So first,
No, I used the measuring card. Yeah, I know I should show it.
so first things first, we claim that the inverse of the f alpha function is simply the f alpha function applied with the inverse of alpha. And similarly, we define the same thing for g, that
Less than
alpha negative 1. And we're able to show this because for all x element of, for all x in G, where G is this generic group we have, we know that
I prefer a feet away.
I'm sure she's probably. I know. I was telling you a word. You something out of us live. You can just look at it. You can say like you're in the process of
Are you, did you not do the?
so simply here we can see that the alpha inverse and alpha are canceling out just to produce the identity, which just leaves us with x. And similarly, we have f alpha
You only have one.
Okay, so but you don't even know if you get your card.
x.
You can't have one in this world.
I can only get a bring my a card here once I buy a card myself, so that's probably not that like
So similarly, we have the same fact, simply just composed in the other direction. Once again, alpha and alpha inverse are canceling out just to produce the identity, which leaves us with x. So in this way, we've shown that our f of alpha inverse function, as we've defined, is in fact the inverse of our regular alpha function. And the exact same argument applies for g, just with on the other side. So instead of being on the left of x, it'll be on the right side of x instead.
Yeah, that's what you do.
And for that reason, f alpha is bijective since since the inverse exists.
I guess email center.
So because the inverse exists, it's bijective. So now we're gonna change gears a little bit. And we're going to define a new function. So we're gonna let f from g cross g to g, which sends an ordered pair x, y to x times y. We know that this is continuous since G is a topological group, so we already know F is continuous. And then we can say that F alpha is simply our new function F, but restricted to the set alpha cross G. And because f alpha is simply a restriction of a continuous function, then f alpha itself must be continuous as well. So we've shown that f alpha is continuous, and the argument for G alpha being continuous is exactly the same, just with the replacement of G. So we have shown that both F alpha and G alpha are continuous as we wanted. So now finally we need to show that they're open. Okay, and we know that both F alpha and G alpha are open as well because we've shown their inverses, and their inverses are continuous as well under the same exact argument we used to show that F alpha and G alpha are continuous, which means that if their inverses are continuous, then the function F alpha and G alpha are open. So that has shown all three of these conditions that we wanted to show. Thus, F alpha and G alpha are homeomorphisms. And the next part of this problem is we want to show that G is a homogeneous space. So, to show G. Okay. So, we'll begin by considering any xy in G. For any xy in G, we will consider f y x negative 1 by simply letting alpha equal yx negative 1. So this is defined exactly the same way as our f alpha function, simply just with a different value of alpha. Then we know from the previous portions of the proof that this new function is a homeomorphism. Then if we simply plug x into this function, the x inverse and x cancel out, and we're just left with y. So we have a function from x to y, where x and y are generic, so G is a homogeneous space.